Hey folks, so last time we did the increasing and decreasing in relative extrema, that's mins and maxes, and we still need to finish up oddness and evenness of functions. So an even function is a function that there's a couple different ways to discuss it, but basically the idea is if all your positive x values have the exact same function value as all your negative x values. So like for instance, if I went over here to negative, I don't know what this is, -2, and I went +2, they both have a function value of 0. Let's say that I went here to, I don't know, let's say this is 1, -1. I drop down to my function. This has some y value, let's call it -2. So -1 has a y value of -2, and +1 has a y value of -2. So that's what the idea of an even function is, that the positive x value or the negative x value both have the same function values. Now, when we're talking about odd functions, the positive x value has the opposite sign as the negative x value. So let's say I went back to -1, this would go up to +2. If I went forward to +1, this would go down to -2. See how the opposite signs of the x values have opposite signs of the function value, but they're the same number, just opposite signs. So that's kind of the idea. Now, you can't just say whether a function is odd or even. You always have to say the because, the why. So there's two different proofs, and I don't care which proof you use. You don't have to use them both. I'm going to do them both when we do our examples, just so that you get practice seeing both of them. But you can use either one. You don't have to use them both. So let's talk about the graphical proof. What do you notice? So we always talk about symmetry when it comes to graph. What kind of symmetry does this graph have? Think back to your geometry days. This is what we call reflective symmetry. Now, you can't just say reflective symmetry. You have to be reflective in some direction or across something. So if you're going to use the graphical proof for an even function, you would say f has reflective symmetry in the y-axis. Now, I might use the word around there or across. I'm fine with that, but this is, I think, the correct mathematical phrasing. You have to go ask Miss Robbins or Miss Murphy, our geometry experts, on the language there. Let's go, instead of doing the algebraic proof right now, let's go do the graphical proof for an odd function. So an even function has reflective symmetry across the y-axis. In other words, if you folded this across the y-axis, you'd get the exact same picture. An odd function has not reflective symmetry, but if I took this graph and I rotated it 180 degrees around the origin, you would get the exact same picture. So this has rotational symmetry. So my graphical proof for an odd function would be f has rotational symmetry in the origin. Then we have the algebraic proofs. Algebraic proofs aren't too bad. They really stumped me when I was a kid, but now that I stop and think about them a little bit, it makes a lot of sense. So for you to have an even function, now, or actually for either one of the algebraic proofs, you're going to do the same thing. You're going to plug in -x into your function. So you're going to plug in -x, you're going to simplify things, and in an even function, the function value for -1 should be the same as the function value for +1. So f of -x is equal to f of x. In an odd function, when you plug in negative, remember what we got up here? We got a 2, and then over here, when we plugged in a positive, we got a -2. So they should be opposite signs of each other. So f of -x should be the opposite of regular x. So either case, start off plug in -x. Then simplify. Then, if it looks like the original, If it looks like the original, in other words, if the equation looks exactly the same, you have an even function. To get an odd function, plug in, lights are turning off again, plug in negative x, simplify. So it's the same thing. It's the result that decides if you're odd or even. This needs to be all, I'm going to underline all, opposite of the original. So all the signs would change. This one, everything stays the same. This one, all the signs change around. So let's do a couple examples, and you'll see more what I'm talking about here. So here's our function. Is this going to be an odd, an even, or a neither? So what I would do is I would first try to make a sketch of this using my calculator. This is not one of our family of functions that we know. I know some portions of it. I know that this is going to be a fifth power is going to look like a cubed graph, but anyway, let's graph it. So 2x to the fifth minus 3x to the third. So now my window was I have my window at 5s. Now you can leave your window at 5 or you can make it 10s. We don't need a perfect picture here. We just need a kind of an estimate. So if you're going to do this graphically, make a sketch of your function. Looks like it goes something like this. And then this side looks like it does the same thing. And then my proof would be, okay, so here's my sketch. Is this look odd or even? Well, does this reflect across the y-axis and have exactly the same picture? Of course not. If you rotate around the origin 180 degrees, do you get the same picture? Yes. So this is an example of an odd function. Our proof would come in two formats. I'm going to do the algebraic proof first. So that's f. Maybe I'll pick some different colors here so they'll stand out. So here's my algebraic proof. I take my function and I plug in negative x. So f of negative x equals 2 times negative x to the fifth, subtract 3 times negative x to the third. Simplify. So a negative x to the fifth is going to come out to be negative, and that's going to make this then negative 2x to the fifth. A negative to the third is still going to be negative, so that negative times this negative 3 is going to make a positive 3. And then look at what we want to do from here. We want to compare. Compare to the original function. What do you notice? Well, everything's the same except for the signs. So these are all opposite of the original. Since they're all opposite of the original, we can just go ahead and just say that your function's odd. You don't have to really say a whole heck of a lot after that. If you are going to prove this, well, maybe we should do a little write-up. So we should say something like, since f of negative x equals the opposite of f of x, in other words, that means that all the signs switched around, comma, then f is odd. Let's try another one, or let's just do the algebraic proof. The graphical proof is much easier. So, what kind of symmetry does this graph have? This has rotational symmetry. So we would say f is odd because f has rotational symmetry in the origin. You may not just write that f has rotational symmetry and call it good. It has to have specifically rotational symmetry around the origin. All right, hopefully you got kind of the idea from here, but we're still going to do a couple more examples. Let's first get a picture of what this graph looks like. So 2x squared Subtract 8x plus 5. Okay, now this is interesting, right? We've got some symmetry going on, or I think there's some symmetry going on. Looks like there's some reflective symmetry, but does it have reflective symmetry across the origin? Sorry, across the y-axis? No, it does not. It does not. So we're out of luck there. So we would say, oh, I'm going out of order. Oh, geez, this says 5. I got to change the numbers of these. So I should have done this one next, I think, but oh well, we'll go with this. So I've got now a graph that looks something like this. I definitely have some symmetry, but I definitely have reflective symmetry, but it's not across the y-axis. So this doesn't have rotational symmetry, doesn't have reflective symmetry across the y-axis, so this would be a case of neither. This is neither odd nor even. Let's do our proofs. Start with the algebraic proof again. So that means you take negative x and you plug it in. So this would become 2 times negative x squared minus 8 times negative x plus 5. Clean this up. So that negative would get canceled out because there's 2 of them. So this would become 2x squared. A negative 8 times a negative x would become a positive. And then that 5 doesn't change because it doesn't have an x with it. Now I compare to the original. And when we compare, we notice that the first thing didn't change signs. The first term didn't change signs, but the second one did, and then the third one didn't. So this is not, this is another proof that this is exactly what we call neither. Same. This one was opposite. This one is the same. So it didn't all switch, and it didn't all stay the same. So we would say something like, since f of negative x does not equal f of x, and f of negative x does not equal negative f of x, then f is neither even nor odd. Oh boy, I don't have a lot of room for my graphical proof. Luckily, in this case, it'll be a lot shorter. I don't have to write as much. So let's say, so does our graph have reflective symmetry across the y-axis? No. Does it have rotational symmetry around the origin? No. So that's going to be our argument. F has neither reflective nor rotational symmetry. Didn't have a lot of room there, but squeezed it in. You don't have to do both of these, just as a reminder. You do not have to do both of these. You can choose which one you want to do. Maybe I should write that at the top. You do not have to do both proofs. You do not have to do both proofs. Pick one and go with it. Once you've proven it one way, you don't have to you don't have to reprove it the other way. All right, let's finish up these last two. You can kind of guess just by looking whether they're odd or even. But I'm going to graph this one just in case. I'm guessing this one's even. X to the fourth minus 2x squared. Subtract 3. Yep, that's even. So I'm going to try to make a decent sketch of that. This is an even. Let's do our two arguments y. Start with my algebraic proof. F of negative x equals negative x to the fourth minus 2 times negative x squared minus 3. I clean it up. That's going to square. That's going to fourth that negative, which will make it positive. That's going to square that negative, which will make it positive, so that stays negative. Now don't forget, we need to compare back to the original. And we notice that everything stayed the same. So we'd make a little argument, since f of negative x equaled f of x, then f is even. And let's do a graphical proof. Since f has reflective symmetry in the y-axis, comma, then f is even. Notice I just didn't say I had reflective symmetry. I had reflective symmetry in the y-axis. All right, why don't you pause here and try the last one? See how you did. Make a sketch. I'm guessing it's going to be a neither because one's cubed and one's squared. 1/2 x cubed minus 3/2 x squared. Try to make a decent sketch of that. All right. Yep, we know this is a neither. Now we need to prove it. We can't just say it's neither. We have to prove our result. So our first proof is, I'm going to do it algebraically. Like I said, you don't have to do it both ways. F of negative x, so that would be 1/2 negative x cubed minus 3/2 negative x squared. A negative cubed is still negative, so that's negative 1/2 x cubed. A negative squared becomes a positive, so this will stay as a negative. Then we want to compare back to the original. I just used this one. I feel like I just used that one. So this was opposite. This was same, which means it's neither. So we would write a little argument. Since f of negative x does not equal f of x or negative f of x, then f is neither odd nor even. And then last one here, let's do a graphical argument. Since f has neither reflective nor rotational symmetry, then f is neither And you can add neither even nor odd if you have more room than I do. I don't. I'm going to stop there. All right, so lots of stuff going on this section. We have all this increasing, decreasing stuff. Chances are you're going to forget how to find, keeping track of who's your X values and who's your Y values. It's real easy when the graph is done for you. I'm not going to give you the graph. I can tell you that right now. I only did this to kind of give you the idea of how this works. You need to be able to do this graphically. So this would be a great example to test yourself on if you already forgot how to do it. And then we've got oddness and evenness. The arguments, you don't have to do both of them. Excuse me. You don't have to do both of them. You just pick which one you want to do. All right, good luck.